Hello everyone, welcome once again to this class. Uh, so we were going with the chapter magnetic effects of current, and we had already done a few things like derivation of magnetic fields using Biot-Savart law, and also we had learned about the Ampere circuital law, right? So Ampere circuital law is another process for finding the magnetic field, and I told you that this law is applicable under one restriction. And what is the restriction? The restriction is that you need to know about the direction of the magnetic field from the beginning. Okay, if you do not know the direction of the magnetic field, you will not be able to apply the Ampere circuital law. Okay, so in the last lecture we had found the magnetic field around a circular wire, right here. So what was the concept? The concept was we need to take a closed path, right? We need to take a closed path, and then the line integral of the closed path, the line integral of magnetic field around the closed path, which was represented by B dot dl, E vector dot dl vector. This is called the line integral of magnetic field vector around the closed path, which is equals to the mu 0 times current which is threading through the closed loop. This was Ampere circuital law. Today we will use this law again for finding the magnetic field for a current carrying solenoid. Okay, so today's topic of discussion is magnetic field at the axis of a current carrying solenoid. Okay, so hopefully all of you know what is a solenoid, right? What is a solenoid? Hopefully all of you know. So the solenoid is nothing but a large number of turns of current carrying wires. So suppose you are having a large number of circular turns are there. How to make this kind of thing? Suppose you are taking a iron rod, okay, like this, iron rod, okay. Then suppose you are rotating or you are covering this iron rod with circular turns, many turns. Okay, so if you make a system like this, then it will be called a solenoid. Okay, so one more thing is important: the wire should be insulated. Okay, the wire should be insulated. Okay, so this is a system solenoid. Understood? So current comes in from one end, and in this manner the current is moving on. So hopefully you are following what is a solenoid. Okay, so the characteristics of a solenoid is you need to know about the length of the solenoid. Suppose the length of the solenoid is L, and how many turns it contains in its length. Suppose there are N number of turns. Okay, so suppose there are N number of turns, and the length of the solenoid is L. Okay, so these are the two parameters. and depending on the circuit or depending on the battery you use here, the current will flow. Okay. So as we know that the current has a magnetic effect, so this solenoid, there will be a magnetic field around the solenoid also. Now in our class 10 level also we have studied about current carrying solenoid, isn't it? So if you remember the concept, the solenoid does behave like a bar magnet. Okay, current carrying solenoid behave like a bar magnet. What is a bar magnet? Bar magnet is simply a rectangular bar. Okay, a bar magnet is simply a rectangular bar having north pole and south pole, right? So if you remember the characteristics of a bar magnet, the bar magnets have highest strength at their poles, right? So if you remember, if you bring some iron, the powder of iron, okay, you will see that all the powders, iron dust, will be attached at the two ends, right? All the iron bars will be attached at the two ends. There will be hardly any powder in the middle part. There will be hardly any. There is nothing actually. So this is general knowledge, right? General knowledge of a bar magnet, that the bar magnets has the highest strength at their poles and negligible amount of strength in the middle portion. Okay. So if I draw the field lines, right? Field lines are what? Field lines are the lines of force actually, in which direction the magnetic force does actually exist. Okay. So if I draw the field lines for a bar magnet, you will see that suppose this is north pole and this is south pole. So for a bar magnet, the magnetic fields starts from north pole and it ends at south pole. Okay, let's remove this part first. Actually, if I draw it properly, right, it will look like this. And also, so this is the magnetic field lines are like this one. So if you see, this portion are basically fieldless. Near the middle part of the bar magnet, the magnetic field lines are almost nil. There is nothing present. Okay. So why I have drawn this thing? Because I have already told you, to apply the Ampere's circuital law, we need to know about the direction of the magnetic field. These lines of force are what? These are the direction of the magnetic field for a bar magnet. Okay. So now if I go back to the solenoid, suppose this is the solenoid. Okay. So suppose current is going in from this side and going out from that side. Okay. So this bar magnet actually behaves like this solenoid actually behaves like a bar magnet. So one of its end will behave as a north pole and one of its end will behave as a south pole. Now which one will be north pole and which one will be south pole? For this, one more concept is important. Suppose whenever you are looking at the solenoid from the front, okay, suppose you are looking at the solenoid from the front, so you will see a circular turn like this. isn't it? So you will see a circular turn like this. Okay, and suppose the current is rotating in this direction, which is anti-clockwise, right? This is anti-clockwise. Okay. So see, for anti-clockwise rotation, I have drawn it an N inside it, right? So it means anti-clockwise corresponds to North Pole. So whenever you will see in a circle the current is looks like anti-clockwise in rotation, that particular N will behave as a North Pole of the magnet. Okay. Whenever you are getting a circular turn and the current is in clockwise direction, then okay, so for clockwise, see, it is equivalent to a S. So clockwise rotation simplifies it is a south. Understood? It is clear or not? So whenever you will see a circular turn, looking at the rotation of the current, you will be able to say either this pole will behave as North Pole or South Pole. Okay everyone? Clear this part? Okay. Now, so if I take this example, if I look from this side, the current is, see, this is going like, right or not? So if you turn it around you, so you are getting what? You are getting like this, right? If this part turns towards you, you are getting like this. So this is what? This is anti-clockwise. This is anti-clockwise, right? So anti-clockwise means North Pole, right? North Pole. So this end will behave as North Pole and this end will behave as South Pole of the bar magnet. So this North Pole or South Pole does depend on the direction of the current or the rotation of the current. Okay, this part is clear. Now we will move towards applying the Ampere's circuital law for finding the magnetic field inside the solenoid. On the axis means inside the solenoid. So if I draw the magnetic field lines, okay, so the magnetic field lines will look like this. Magnetic field lines will look like this. I am just drawing one line for your convenience. Okay. So see, inside the solenoid, the field lines is actually directed from south to north inside the solenoid. Okay. Is it clear, everyone? Now let us draw. Now we have to do what? We have to find the magnetic field. So we have to draw a closed path. We have to draw a closed path. So let us draw a closed path. Okay. I am making it a very simpler one. Suppose I am taking a closed path like this. A rectangle. Closed rectangle. A, B, C, D. Okay, A, B, C, D. Clear or not? And suppose there are n terms. So according to our what Ampere's circuital law, we can write closed integration integration of B dot dl equals to mu 0 times. Now as there are n turns, so the current will be Ni. Okay, as there are n turns, so current will be multiplied by n. Total current is Ni. Okay, so this is basically the Ampere circuital law written over here. Now we have to break this closed integration in 4 different parts. So it can be written as integration of B dot dl for the part AB. Okay, I am breaking the closed path rectangle in 4 different segments, plus integration of B dot dl along BC. Okay, plus integration of B dot dl along CD. Okay, and plus integration of B dot dl along D. Isn't it? Okay, so equals to Ni. So what we have done here, that we have just broken the closed path in 4 different segments. Now we will deal with these 4 different segments individually. Okay. Now first of all, look at the part for CD. Okay, look at the part for CD. For CD, as from the drawing of the magnetic field, we know there is no magnetic field near the solenoid. So in this region there is no magnetic field, here B is 0 in this region, right? So integration of B dot dl for the part CD will be 0. Are you getting my point? So for this part we are getting 0. We need to mention the reason. What is the reason? Reason is near the solenoid there is no magnetic field present. Okay, so this part we have dealt with. Now 3 parts remain. Okay. Now look for the part BC and DA, right? So whenever you are taking the closed path, the closed path has a direction, na? The closed path is also having a direction. So the direction of the DL, okay, I am writing it in the up here, right? The direction of DL vector for BC and DA are in opposite direction, isn't it? So for the part BC and DA, the DL vector are in opposite direction. It is clearly visible from the diagram. So we can simply write that integration, whatever may be the value of B, the value of B will be same for both the 2 sides because they are at symmetrical position. BC and DA are in symmetrical position. So the value of B will be same for both the 2 sides, isn't it? But what is the difference? The difference is in the direction of DL. So we can simply write that B dot dl for the part BC will be negative of B dot dl for the part DE. Are you getting my point? So as for these 2 parts AB and BC, magnetic field B is symmetrical, but there is a difference in the direction of B. sorry, dl, difference of direction of dl. Okay, so we can write B dot dl is minus of B dot dl at dA. So this equation gives you what? The BC is minus of dA, so this part and this part will get cancelled, isn't it? So whenever you will apply this equation, this part and this part will get cancelled. Understood? So we have already mentioned the reason above it, right? So what does actually remain? So see, this part is 0, these two are cancelled each other, so only the remaining part is B dot dl along AB, which is mu 0 n I. Okay, which is mu 0 n I. Okay everyone, now it is very easy. So as I have already shown you, the magnetic field is in the same direction of dl, isn't it? Whenever we come to the point inside the solenoid, the magnetic field and dl vector are in the same direction. Okay, so it will be simply B dot dl cos 0. Okay, so I am removing this part. So you will simply get D will outside the integration, cos 0 equals to mu 0 n I. This is along AB. Okay, so cos 0 is 1. B, integration of dl along AB. So basically integration of dl along AB will give you the total length of the solenoid, which is L equals to mu 0 Ni. Okay everyone, understood? So we are getting the resultant B in the axis of the solenoid, which is mu 0 Ni by L. Okay, so this is the expression for the magnetic field inside a solenoid. Sometimes it is written as in this manner, mu 0 small n I. What is small n? Small n is n by L. It is number of turns per unit length. Okay, so the expression of B is like this. Okay everyone, so this derivation of magnetic field for the solenoid, inside the solenoid, is very important. Okay, so whenever you are doing the derivation, you need to mention every assumption that I discussed over here. Okay, why each and every part, how each and every part are actually dealt with. This one, how it becomes 0, how these two parts cancel each other. Okay, we need to mention all of these things. Okay, then we are getting the result that D equals to mu 0 small n. Okay everyone, so and one more thing is there, which is called toroid. So this is nothing different. What is toroid? I will explain just. Okay, one more thing is there, which is called toroid. Okay, what is toroid? Toroid is a circular solenoid. Okay, so if you join both end of the solenoid, like suppose you are having a spring, the solenoid is like a spring, right? If you connect the both end together, it will look like this now. Isn't it? So basically this is called a toroid. Toroid is endless solenoid. Like you can remember like this. Toroid is one kind of endless solenoid. So it looks like a circular thing. So if you are asked to find the magnetic field inside a toroid, so you are taking a closed path like this. Now the closed path is very simple, right? Now the closed path is the circular one. So simply you can write again mu 0, total number of turns, suppose capital N into I. So again B is in the same direction of the dl. So B closed integration of dl equals to mu 0 n I. Now P into, now what will be the length of this circular path? It is obviously the circumference 2 pi r mu 0 n I, isn't it? So B will be mu 0 n I by 2 pi r. Okay, so it is also same formula. If you see, if you are asked what is the length of the solenoid, the length of the toroid, length of the toroid now is the circumference. So again, actually what it is there, it is again the length of the solenoid type of thing. So length here actually circumference. Okay, so the formula is nothing new, only the difference is in the way of derivation, because here the circular closed path is a circular one, but in case of solenoid we need to take a rectangular closed path. Okay everyone, so this is all about the derivation of the application of Ampere's circuital law. You need to know about all kind of derivation. These are useful in the exams. Okay, in the next class I will deal with some numericals which will be regarding the Biot-Savart law as well as Ampere's circuital law. Okay everyone, so this is all for today's class. In the next lecture we will deal with some numericals. Okay, thank you, have a nice day.